Welcome to another tutorial covering the use of Curvy version 2.0. In this video, we will be covering one of the most powerful systems in the package – generators. Generators are game objects with a Curvy generator component. Generators are responsible for a network, or so-called node graph, of modules. Modules are child objects with components inheriting from CJ module class. But that's not really explaining much, does it? So, let's start with some simplifications and basic examples. Without going into much detail, a generator takes some input, usually spline data, processes it, and outputs a result. You have probably seen some examples of generator use in the sample scenes provided with the package, like scene 21 with a road loop or scene 25 with a railroad. Let's open one of them, situated here in the scenes folder, and take a look at it. You can take a look at the internal structure of a generator by selecting a game object housing it and using the Edit button. It is situated in the component inspector and on the toolbar. Let's click that button. Okay, that looks pretty scary. But don't worry, you'll learn to build generator graphs like those in no time. For now, let's start with the most basic generator possible. Let's create a new empty scene. Then, let's create a generator object through the hierarchy context menu. Situated here, you can see the generator option. Then, let's open it. As you can see here, it's empty. You can toggle some help information with this button in the top right corner. In a way, generators are similar to other node systems like ShaderForge and Playmaker. You add modules, you link them, inputs travel through modules and turn into some result. So, let's create a basic graph. As we see from the help box in the corner, there is a context menu available. Upon opening it, we see the Add and Add Template options. As we don't know yet which individual modules we should choose, let's study a template first. Specifically, the shape extrusion template. Upon clicking it, we see it created in our editor view. First, let's attempt to move the modules around a bit. You can do so by dragging the headers, as you can see here. The structure of this generator graph is pretty simple. It accepts a path and a cross-section shape, generates a volume out of them, and then generates a mesh out of that volume. Let's see it in action. For the generator to work, we need to fill all the inputs. The template comes with only one input field. As you can see here, input spline shape module already has a spline in it. You can see it in the hierarchy tab under the module game object, here. Or you can simply select it by pressing the select button in the module inspector. The module called Input Spline Path, however, is empty. You can fill it by dragging a standalone spline from the hierarchy view into the empty slot here, or by simply clicking the plus icon next to that slot, which will create a new spline. As you can see now, with all the inputs filled, the generator starts working and successfully creates a mesh from them. Inputs don't have to be parented to input module game objects, like we see in here with this newly created spline. But sometimes it's useful to do so, as generators can become prefabs. Including all input game objects inside the generator hierarchy allows you to preserve them as a part of a prefab. Let's try tweaking the results now. For example, let's take a look at the spline used as a shape input. In our case, that spline object is using a circle shape component, which automatically controls the points and handles of that object. As you can see here, we can control it using the traditional inspector or through the module interface available in the graph editor, as you can see here. Input Spline Shape Module Inspector here provides us with a quick way to switch between components, dictating the shape of a cross-section. There are circles, boxes, and so on available, like you can see here, with easily tweakable parameters, like width, height, radius, and so on. Even a star, which you can tweak into ropes and many other shapes. Let's get back to the circle, let's say with a radius of 0.5. As you can see, the generator updates the mesh every time we change something. We can of course, use a completely freeform spline, independent from shape setting components like those. Just plug in a standalone spline or click the freeform toggle here, then edit the control points and other spline attributes directly, like we can do here. Moving on, we have the shape extrusion module. It turns our cross-section and the path into a volume, and therefore allows us to configure how that interpretation is performed. You can alter the path resolution or cross-section resolution, as you can see here. The angle threshold, as you can see here. You can ask the generator to only use a limited part of a spline, like here, or a limited part of a cross-section. Independently configure cross-section resolution, alter the scale of an extrusion, create a hollow surface, and so on. I will not go into detail about every single option on every single module in this video, as information like that is better presented via text documentation, which conveniently can be accessed through the help button attached to the top right corner of every single module. Let's try to click it. And as you can see here, we are transferred to the browser page. So let's return to the fundamentals of the generator then. As you might have already noticed, input and output slots are color-coded and type-labeled, so even if you aren't familiar with the function of some module, you can still build a working generator with it. In case of a shape extrusion module, it accepts a path and a shape, and outputs a type called volume. Naturally, to continue building our extrusion graph, all we have to do is to find a module accepting the volume input, which happens to be the volume mesh module. Here, the volume is turned into a so-called volume mesh, which contains vertices with UVs, material IDs and other things, making up real geometry. It's still not a true mesh you can render for. To get an object you're seeing here in the scene view, we have to convert this easily modified volume mesh entity into a traditional Unity mesh entity. We also have to create a game object with mesh filter and mesh renderer components attached, if we want to house and render it, which is what the final module in our graph is doing. It's called create mesh, and it takes our easily modifiable volume mesh and converts it into Unity mesh. It also creates a game object with aforementioned components and plugs our mesh into them. So, I hope that the generators aren't such a mystery now. Those are just simple sequences of modules transforming simple data types. Now, let's get back to that huge graph in the scene 25 and try to read it. First, we'll open the scene and examine its contents. It's situated here. In this scene, we have 3 splines. Let's change some options to see it more clearly. First, we have the main track path here. Then we have the shape for the bridge cross-section. Then we have the shape with the rail track cross-section. And those are used in 4 extrusions. First, the rail track itself, then the bridge, and then 2 wires, here and here. Aside from that, the scene is populated with spline-based objects. There are wire supports, you can see here, those little posts next to the track, and finally sleepers, those concrete things under the rails. If you take a closer look, you can even see that there are 4 randomly placed types of those sleepers. Believe it or not, whole scene is spline-based, with exception of the ground plane. Now, being familiar with the output of the generator in the scene, let's take a look at its structure. The generator is situated in this object. Let's open it. Oh, it looks like I forgot to mention another spline shape in the scene, with a wire cross-section. Here. Anyway, as you can clearly see here, at the top left corner of the graph, we have input modules with all the aforementioned splines plugged in. Railroad path, rail track shape, bridge shape and wire shape are all here in those 4 modules. Moving on, those 4 input modules feed 3 shape extrusion modules, one for the rail track, one for the bridge, and one for the wire. Take note of some configuration differences here. For example, the bridge extrusion is set to start at a certain position on the spline and continues for 30% of spline length, which is why it ends where it ends and starts where it starts, instead of continuing through the whole rail track spline. Notice how path optimization settings are different too. Rails get new vertices inserted whenever 2.5 degree rotation threshold is crossed, while wires, to reduce the poly count, only get new vertices every 5 degrees. Cross-section settings, again, are also different. As you can see here, for example, wires have lower cross-section resolution and don't use advanced UV data. Following the rail track branch further, we see the familiar module sequence. It gets turned into a volume mesh and then into unity mesh in a creation module. Settings of the volume mesh module here are pretty interesting. First of all, the volume is split into an array of volume meshes every 100 meters to aid with cooling and reduce per mesh poly count. The track is also using two materials, one for the ground and one for the metal. Let's take a closer look at that. Here we can see the metal material. Here we can see the ground material. But how can the volume mesh know which vertices should use which materials? Well, that's where control points come in handy. They are useful for more than just defining a shape of a spline. They can also contain information about texture coordinates, material IDs, and hard edges, and can become vertices after rasterization in a volume. Let's take a closer look at the track cross-section spline. As you can see here, its control points contain material ID information. Ground material is 0, as you can see here, and rail material is 1. And as we go through the control points, we can see how that number is changing. Control point 0, control point 1 contain material ID 0, control point 2, where we start. Control point 2, where the rail starts, contains material ID of 1, material ID of 1 continues here and here, then we return to 0 here and here, then to 1 here, here and here, and finally back to the ground for the last control points. Let's take a look at the track. We get the ground here, then the rail here, then the ground again here, then metal again here, then the ground edge again here. Oh, those material IDs really work. You might also be noticing that the texture mapping on the track is pretty elaborate. Let's take a look at the material. We have a simple square texture with two tiled strips, solid ground on top and a transparent edge on the bottom. How can the volume mesh module know the texture coordinates we want on all those vertices? We want the bottom strip here and here, and the top strip here. Again, the module can't know it, so that information is simply embedded in the control points. You can, of course, auto-generate UVs without the need to define anything in the control points, but sometimes precise control over UVs is a necessity. You can take a look at the scene 26 later, which contains a very elaborate example of control point-based texture mapping. So, taking a look at the cross-section again. Here we have coordinate of 0 on the control point 0 and the coordinate of 0.5 on control point 2. As it's also a material edge where the rail metal starts, as you can see here, we have another coordinate we can input. In this case, we use 0. We then go to the control point 5 here, which again switches the material ID from 1 to 0 and input the coordinate of 1 for the rail metal here, making it proportionally stretched over the rail, like this. Then we input coordinate of 0.5 for the start of the ground segment here, and the coordinate of 1 for the end of the ground segment here. And afterwards we repeat the sequence we have seen before, with the stretching from 1 to 0 over the second rail, and with the stretching from 0.5 to 0 for the opposite slope. It's quite a mouthful to call out all those coordinates, but it's a pretty simple workflow, once you get the hang of it. That's quite a lot of power in a few simple inspectors, isn't it? You can use any number of materials mapped in a very precise way to a very precisely shaped extrusions. Let's return to the graph. The bridge extrusion is pretty similar to the track extrusion. Again, it's using custom texture mapping to align the seams on it with the texture, as you can see here and here. The only significant difference in its graph is the use of a new module, so-called modifier. It's used quite a few times in this graph and can shift position, rotation and scale of volume meshes. Here I'm using it to lower the bridge extrusion down a bit, to prevent it from clipping into the rail track. The output of the same bridge shape extrusion is used for another module, volume caps, which of course is used to generate those two meshes, here and on the other side here. It's a pretty simple module, you can read all about it in the documentation. Basically it provides some simple texture mapping options and generates the outer surface on the end of an extrusion. Next up we take a look at the wire shape extrusion module. Here we have two wires in the scene, as you can see, but we only use one volume mesh module, as both of them have an identical shape. We then plug the volume mesh output into two modifiers, as you can see here and here, shifting the result to different heights, and then use the output in two create mesh modules to create the two wire objects. That's it for extruded objects. Now to the scattered objects. The structure of a spline-based object placement generator graph is pretty simple. First we need mesh inputs or game object prefab inputs. Here, for variety's sakes, I'm inputting sleepers and bridge supports using prefabs in an input game object module, as you can see here for the sleepers and here for the bridge supports. And I'm using an input mesh module to input the posts mesh as a mesh reference. Second, we need to generate the so-called spots or transforms for those objects will be spawned into. To do that, we need a volume and a set of bounds. You can read the detailed documentation on the volume spots module later, but the gist of its use in this graph here is this. Every single volume spots module is using the output from the same shape extrusion module, from the rail track. From it, it extracts a spline path and volume information required to build those transforms. And then we plug the bounds from the input game object and input mesh modules into those volume spot modules. Let's start with the sleepers. Sleepers get spots with one of the four randomly selected prefabs separated by 0.3 meters each. Roadside posts get randomly rotated spots offset from the spline over the whole spline. Bridge supports get spots distributed on a certain portion of the spline, roughly matching the bridge extrusion area. They are also rotated vertically, instead of being aligned to the spline, as you can see here. They are also vertically offset from the path using this field. Wire supports get vertical orientation too, as you can see here, and are distributed over the whole spline, as you can see here. And finally, wire holders, those C-shaped sinks between two wires, get a simple vertical offset and distribution over the whole spline. They are also randomly rotated by 180 degrees. And that's it. Beyond the spot generation, all we have to do is to plug the outputs to modules, creating game objects or meshes. With that, we are finished with the graph. For example, this module creates the bridge supports. That brings our generator overview to a close. We have examined the setup of a small and simple extrusion, learned the basics of generator structure and module use, and then examined a very complex generator with a real environment use case. I encourage you to check the documentation of the modules you have trouble with and to ask any questions in the forum thread linked in the video description. Generators can be pretty confusing at first, but they are an incredibly powerful system capable of driving the scenes of staggering complexity, so investing time into learning them definitely pays off. See you next time!